we will take up the details of doing the image coding of video and the critical part of orthonormal basis of cosine functions in 2D, how it is used. We had a glimpse of how it is finally broken down to small 8 cross 8 blocks, and the 2D basis function of DCT of 8 cross 8 block is used to code this, and we will see how it is done and what happens when it is done and how it looks finally and so on and so forth. Okay. This is also built into what is called standards. JPEG is one standard, MPEG is another standard. You will get plenty of audio and video coding standards. So, this task is using JPEG image compression standard, which says convert RGB to YIQ or YUV, and we will see what is the subsample. Do DCT on image blocks, quantize the result, further compression of doing zigzag or run length coding. You can also do Huffman code and compress. So, basically once the data is coded, you further compress so that you get a very tiny data size with which your entire movie or audio is coded and captured. Okay. So, the idea is clear. So, you take, for example, you take this image. So, image, famous image in for over many years. This is one image, and I have taken a 8 cross 8 block here, and on a 8-bit 8 cross 8 block representation, the equivalent values are 200, 202, 189, so on here. So, out of this 8 cross 8, these are the 64 numbers on which I do the 2D DCT. 2D DCT I apply. What did you expect when you apply DCT on a data x of n? You apply DCT on that. What you get is data which is on the lower spatial frequency, that gets coded, rest of it is close to 0, very small. And I said we do it for both rows and columns, the top left quadrant gets occupied. So, when I do the 2D DCT, which is basically an 8 cross 8 matrix, this is an 8 cross 8 matrix, data matrix 8, and I apply a 8 cross 8 DCT. Once I apply on the rows and columns separately, I am going to get another finally 8 cross 8 matrix, coded matrix, also size 8 cross 8. This is what the 2D transformed version or coded version looks like, and you will see these numbers here 186, 187, 187, 188, whereas these numbers are very small here 4, 3, minus 2, etc., etc. Whereas the top left corner 1, 2, 3, 4, this seems to dominate compared to this. Okay. So, this is the 2D transform data on which I want to apply quantization. What quantizers? I am going to apply quantizer for illumination. This is the quantization table built in for illumination, which is the y component. The CBCR components are here, or y, this is y, these are the I and q component, whatever you want to call. You can see here 1, 2, 3, 4. These are smaller numbers compared to this. So, you go back to the DCT transform, these are big numbers, which means information is very important. Therefore, big numbers are quantized with smaller numbers, so that most of the data is retained, whereas very small numbers are divided by big numbers, so that when you quantize they all go to 0, You see here, after quantization you will see that almost the top left corner only one here, except that all other things are 0, which means approximately straight away at first step you will get between 75 to 85% compression. The question is not whether the compression is high, the question is what happens when you use this to reconstruct. How accurate is the reconstruction is the final proof of the success. Okay. So, this is really what it is, this is all the data that you are going to use. This data is transmitted. Of course, in the actual package some more compression is done, because I am not going to code like this, I am going to code like this, zigzag coding. So, you will have run length code, long sequences of zeros, all that, do not worry. Conceptually it is not with linear algebra, this is the linear algebra part. So, what I do, I store this, either store or transmit, and when I want to use it I have access to the same illumination table, which means I use corresponding locations to re-multiply by that number. So, I have 32, I want to multiply 32 by 16, the next number by 11, so on, and so this is the quantized data. This also again 75% is simply zeros, nothing would have been, it would have said create a block of 8 cross 8 with these numbers, rest is 0, it will recreate. Only this much is needed to send or store. You recreate this, requantize, then I want to know the original. So, I do inverse 2-dimensional DCT, 2D DCT, inverse DCT I do on this, I get this data. All these which were zeros gets filled up with very big numbers. How do I know how good is this? I take this, take the original data, subtract location to location, I get this is the error. You see the maximum value of the data 205, here 210 here. 210 is the largest size data, and you get errors, which is the largest error is 7. Not only that, in near neighborhoods you have errors of opposite kind, right. Not only the errors, most of the errors are small, see here, block of small errors, row of small errors. Errors are small, errors are of both kinds, distributed. This is the reconstructed data. Now, if you look at the original data 200, you got 199. Can you say, can you even recognize the error here? Can you recognize that this is an error? And there are how many? 64 8 cross 8 blocks, 64 8 cross in one frame in one part, that is Y alone. For CB and CR, the chromisons table is also this. Again here you can see the small portions, top left corner has small numbers, whereas all others are, because I is poorer for color than illumination. This is another psychological aspect used. Colors need not be coded as accurately as illumination. Okay. So, you save there also, you do that, and as usual you want to make a good product, you have to simply pack everything, you pack. You start the image, each frame, end of image. For each frame you have tables, headers and scans. Each scan has its own tables, header and segment. Each segment has blocks. The whole thing is packed into a Bitstream and it looks like this. So, when you make a DVD, most critical part, of course you have to do lot of dressing around, a lot of cosmetics for all that, but the critical part is 2D DCT. It works. This is what makes it work. And 2D DCT is basically taking data, representing data using orthonormal basis, which is the cosine. So, when you use DCT, and of course there are extensions of this, the MPEG audio and video. Also uses this. In many cases they use even the next version, the orthonormal version, which is wavelet basis. Okay. So, basically orthogonal and orthonormality basis using orthogonal and orthonormal functions are very critical to not just this, many other applications in engineering field. Okay. So, summary of making the DVD: high orders of compression needed, it should yet preserve the quality. This is where DCT wins over many other things. Use transform techniques, in particular DCT, because it is efficient, real and simple. Use systematic steps, which is what algorithms are all about, compatible with how you process image. You have various quantization, lookup tables, file format, all that. Encapsulate the whole thing and package it as a DVD. You use ideas of electronics and communication and computer science, a little bit of psychology. For example, the persistence of vision clearly tells that you have to code with greater than 20 frames a second. But there are other applications, for example, your formula races and even Jackie Chan movies and so on and so forth. You have to work between 40 and 200 frames a second, wildlife photography, all that. Okay. So, there are other cases, but for most common entertainment, popular one this, and human limitations used as an advantage. For example, humans can never detect small errors are not registered by human vision. Okay. Eye is much less sensitive than ear. Ear can pick even smaller errors than eye. All this works because appropriate mixture of mathematics, particularly the linear algebra using DCT as a basis, projections, eigenvalue eigenvector of real symmetric matrix, orthonormal basis, which itself this thing for representing data. Okay. So, it codes very well, as I said, it codes, takes this thing 1/4, sometimes even the top 1/8. So, straight away 87.5% data compression achieved, 87.5% of the data not used, only 12.5%. Yet distributed errors, and this is the amazing capacity of DCT which other transforms do not show, particularly DFT. Okay. We will also look at some more applications using concepts of linear algebra, because this is again just a glimpse of things, whereas the DVD was done in reasonable detail. The idea of least square error, again as I said, that error was least squared or the minimum square error as it is called, basically another idea of curve fitting. So, you have data points, you want to pass a line which makes these distances, sum of the square of this minimized. That is the idea of mean square error. Okay. So, find a line, that is find the constant c and m given data points x1 y1 all the way to xn yn, find that coefficient c and m such that the line passing through this is such that these lengths L1, L2, L3, L4, L5. So, sigma Li squared I equal to 1 to 5 is minimum, that is find c and m such that this is minimum. This is in essence the idea of even regression and other things, but not necessarily straight line, you can have a polynomial fit. Okay. What is interesting is the origin for this seems to have been from Gauss when he was looking at problems of celestial mechanics. Okay. So, Gauss least square and the missing planet, of course he did the problem there not necessarily in xyz coordinate system, but r theta phi. You can do in any coordinate system. We are more familiar with rectangular, but the polar form, spherical form is very used, particularly even in CT scanners. Much of your projection and other things representation is not in xyz, but in r theta phi, simply because the brain seems, most of the organs in the body are spherical or volumetric in that form. Okay. So, let A be a m cross n matrix. The following statements are logically equivalent. Equation Ax equal to b has a unique least square solution for each b in Rm. The columns of A are linearly inverted. The matrix A transpose A is invertible. When these statements are true, least square solution is given by the distance from B to the so called least square error of this approximation. We will see that here. Okay. The other interesting application, we will come to that least square thing, is the famous communication problem which says optimum Wiener filtering. What it means is, I have a signal corrupted by noise, I want to find a system which is a linear system. I get an output which is an enhanced signal suppressing the noise, which means z of t is very close to x of t. How it is done? You take x of t and build a covariance matrix. And solve for the filter coefficients. So, basically it solves Ax equal to b of a different kind, where the A is origin of the A is covariance matrix. Okay. This least square error is used particularly in the anti-aircraft gun problem. Here is I am spotting a enemy plane, I am here on the ground somewhere and I want to fire anti-aircraft gun missiles. Or how do I fire? I estimate a profile and hypothetically feel, based on the observation and measurements, that in some time t the plane is likely to reach here following the trajectory so far. So, I try to hit the plane assuming that it will reach here at some time. Of course, the plane can go like this, the plane can go like this, the plane can go like this, so on, which means the plane can be anywhere around this estimated point, which is really the error, least square error. It can be in 3 dimension, it will be in a ball. So, I am trying to point out here, it can be. So, I want to minimize this so that I really hit the target. This is in essence the application of least square error in target identification, anti-aircraft, missiles, all this today. Okay. And you will see that very frequently used now in the famous Iron Dome thing, which all of you have got exposed on the TV. Okay. This basically multi-target least square estimation. Of course, it uses ideas of Kalman filter tracking, all that, do not get into sophistication. Basically the central point is least square estimation of targets. Again, one of the central points is linear algebra is eigenvalue, eigenvector. They are found applications in civil engineering as principal stresses, and they are used frequently in mechanical engineering as a vibration problem. These are used in structural mechanics where buckling loads and buckling modes. All branches use that, but we will look at one specific application which is very common, all of you do. Suppose I have matrix A, I find the eigenvalues, eigenvectors of this, eigenvalue, eigenvectors of this. One eigenvector is lambda I, lambda is minus I, corresponding eigenvector is minus I 1, and one more eigenvalue is plus I. And please remember, whenever complex eigenvalues, they always occur in complex conjugate pair. So, one eigenvalue is minus I, the other eigenvalue has to be plus I, corresponding eigenvector is minus I plus 1. The corresponding eigenvector for this is complex conjugate of this, because this is the complex conjugate of that I minus 1. Now, in many cases we have problems of the type Ax equal to B, where B is of a very special kind. B is many times x dot, that is the derivative of x. So, Ax dot equal to, Ax equal to x dot or x dot is equal to Ax is a very common thing. Suppose I apply once more, I can get x double dot, I can get x triple dot, so on and so forth. This is how many cases differential equations are solved through linear algebra. We will not go into that detail, but one particular application of eigenvalue, eigenvector is what we are going to take. And the solutions for this is typically the output or characteristic solution is some alpha 1 e to the power lambda 1 t with an eigenvector characteristic plus alpha 1 complex conjugate e to the power complex conjugate t complex conjugate vector. When we do this, something interesting happens. So, if I take e to the power j omega t plus e to the power minus j omega t, the real part if I get is going to be cos omega t, cos omega t. The imaginary part is j sin omega t. Similarly, if I have 2 times e to the power 2 j omega t plus e to the power minus 2 j omega t, I am going to get cos 2 omega t, and another term will be sin 2 omega t. Okay. So, whenever I have complex conjugate eigenvalues and eigenvectors, I am able to generate terms like cos omega t, cos 2 omega t. So, what is cos omega t? Cos omega t can be cos 2 pi f t. F is a frequency. What is cos 2 omega t? It is 2f. So, basically for different things I can generate frequencies f naught, f1, f2, various frequencies by simply having various complex conjugate eigenvalues and eigenvectors, eigenvalue, eigenvector. So, the trick is that I can convert this into hardware, where if I have a circuit with a complex conjugate eigenvalue, eigenvector, and I give some battery signal, output will be a tone f naught, like tone. Some other hardware, same battery signal, I can get f1, all different. This is exactly how a circuit like this is made. I have frequencies 1, 2, 3, A, you can make it 5 or if you want, A, all these 16 2 4 4 16 different circuits and I get a combination horizontal frequency and vertical frequency combined. So, it will be f naught plus f1 and f1 minus f naught. Similarly, f2 plus f3, f3 minus f2, so on and so forth. So, I have 1, 2, 3, 4, 5, 6, 7, 8 different tones. These are called the low group tones, which are all f3 minus f2, f5 minus f4 kind of thing. These are high tones, f0 plus f1, f2 plus f3, so on. So, I have 1, 2, 3, 4, 5, 6, 7, 8. Each one generates a horizontal and a vertical. These are called dual tone and multiple frequencies, multiple. So, DTMF means dual tone multiple frequency. What this is these are basically hardware, linear algebra hardware which generates tones. Tones are generated because you have eigenvalue, eigenvector, complex conjugate pairs of different order. When you convert the whole thing into hardware and convert it into an integrated circuit chip, this is your DTMF chip. So, what is your DTMF chip? Whenever you press that button, it generates tones. That is why when you have a mobile phone and put says pa 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 beep beep, different, each button gives you different tone. So, basically whenever you use a mobile phone and press numbers, you are basically exciting a complex conjugate eigenvalue eigenvector pair. So, this is how important eigenvalue eigenvectors are. Of course, it is to be found in hardware, that is a different issue, but the central point is the fact that this eigenvalue eigenvector, which is a very central concept of linear algebra, is converted to a product. Okay. So, what all of you use as much as or more than the mobile phone? While you just understand that whenever we operate a mobile phone, we are exciting different eigenvalue complex get started, there is even more valuable linear algebra based action which determines much of our progress or mobility. This is also an eigenvalue eigenvector problem with some modifications. We will come to that. So, look at this data x. So, I am trying to solve Ax equal to x. So, I am trying to solve a matrix A, square matrix. If it is not square, I will do a singular value decomposition. That is why SVD is also very important. Let us take the square case. I am solving Ax equal to x, which is a linear algebra linear eigenvalue eigenvector problem where eigenvalue is 1. So, find the eigenvector for which eigenvalue is 1. Okay. For this specific case, the answer is this, but more important, this is heavily computation oriented, therefore, it is more studied under numerical linear algebra. Okay. It is a large matrix with lots of zeros, sparse matrix with lots of zeros. It also has other properties of Markov chain, and what it simply means is I have some data, typically page in a journal or whatever it is, or in a brochure or in a product setting. I look at a page, and the page, when I look, it refers to some other page, it also refers to one more page, that page may have a relation. So, basically information in different pages or different links today are referred to by one and vice versa. So, what I do is I convert this, the relations between 1 and 4, the relation between 1 and 3, etc., all that into a matrix. There may be multiple references. What I do is I normalize it. So, when I normalize it, the highest number will be 1, the lowest one will be 1 by n. Sometimes there is no reference to each other, it is 0. And the interesting thing you will see, this is 1 by 3, 1 by 3, 1 by 3, this is half half, this is 1, this is half half. So, if I add the column, all the column sum is 1. So, whenever a row sum equal to 1 or column sum equal to 1, it is called a stochastic matrix. If row sum and column sum are 1, it is called doubly stochastic. So, basically I create a matrix with web links or page links from one place to another and create a matrix or S matrix in this, which is stochastic, okay. Whereas here it is all row sum is 1, it can be. Now I solve this, find eigenvalue eigenvector for which the eigenvalue is 1. This is the most important modern result of linear algebra, which is called the famous PageRank, which all of you use when you do Google search and other things. So, no other successful technique other than linear algebra is available to solve this problem. So, all of you use PageRank whenever you search Google and other things, everybody has different versions of the PageRank, slight modifications here and there, but this and your mobile phones are the two best examples of how frequent linear algebra is used in daily life. Almost everybody is using, even the most illiterate person in India touches the eigenvalue eigenvector every day in the mobile phone, and most of you students, as hardly any of you do not look at Google PageRank or search for Google, search through Google and you end up with a PageRank algorithm, this thing, okay. So, the world both scientific and social is filled with applications using linear algebra concept. As the world moves towards data centric life, more applications using linear algebra is only to be expected. We will have more and more. While concepts is what we learn in this course and many other courses, numerical linear algebra and algorithmic linear algebra is what is eventually used in products, okay. It is safe to say that future will be dominated by combinations of linear algebra, statistics and optimization. This combination has another modern label called machine learning or data analytics. So, what people call machine learning and data analytics is also this. So, in conclusion, linear algebra is critically important. Linear algebra is amazingly useful. Study well, work well, you have to solve problems, solve numerical problems. That is the best way to build up from this course, okay. Thank you very much. Please again let me emphasize, it is very important to learn linear algebra well, very useful in applications, learn well by solving numerical problems. Later you can go into so many packages available through Python and all this scikit, that this, so many things are available today. But before you go to those packages which will solve large size problem, you must be able to solve small size problems on pen and paper and be very clear how you are solving and why it is getting solved, okay. Thank you very much for all the attention.